The matrix. It's really nothing more than a two-dimensional vector that has rows and columns. And it looks like this. We're going to be using these big brackets that we've been using for vectors, but now we're going to put them in this funny way. I always thought this looked kind of weird, by the way, because it looks like you're carefully bracketing the left and right sides to make sure that nothing can get in. But we're not bracketing the bottom and the top, and so stuff can get in and out and leak through there. So I always thought that was weird. But anyway, I've gotten used to it now. We're going to be using capital letters to denote matrices, like maybe the capital letter A, and we're not going to put any kind of thing on the top like we did for vectors, so a little inconsistent there, but that's how we're going to do it. And let me just make a matrix 3, 2, 9, 6, 1, 4, 3, 5, 0, negative 2, pi 9, okay? So a matrix has rows and columns, and as I said in the last lesson, it is important that you learn these terms and which way they go. So right there is a row, and this matrix has 3 rows, and right here is a column, and this matrix has 4 columns. And we are going to refer to this as a 3 by 4 matrix. You always list the number of rows first, then the number of columns. It's always going to be rectangular-ish in shape. You can't have a triangle one, although interestingly we're going to define something called a triangular matrix, and you'll see why it's called that in a little bit. But this is essentially all it is, and it's amazing how much complexity this packs into it when we start looking at its properties. One thing we will sometimes do is we will refer to an element of the matrix. I might say element 1, 2. And again, we're always going to give it the row number first, and then the column number second. So if I say, hey, what is A of 1, 2? That is going to be the number 2, because that's row number 1, and that's column number 2, right? Now, right away, we're going to get into hot water with our Python versus R thing. So you'll remember that in R, all of the indices of a vector start with 1, which is just how you learned how to do it in childhood. 1, 2, 3, all the way up to the number of rows, or the number of elements, or the number of whatever. In Python, for some good reasons, but you don't need to understand those reasons now, it starts at 0 and goes up to the number of rows minus 1. So if you have a 10-row matrix, those rows will be numbered in R 1 through 10. In Python, they'll be 0 through 9. So the question is, when we're not dealing with a programming language at all, when we're simply looking at the screen, and we're talking about a mathematical operation, a mathematical object with mathematical notation, how are we going to number the rows and columns? And the answer is I'm probably going to be inconsistent. I'm going to try to stick with the R way because most mathematicians use that. They start with 1 instead of starting with 0. I may occasionally slip, so sort of be on the lookout for that, and it's good to kind of train yourself to be on the lookout for that because, like I said, that's one of the key differences between languages, believe it or not, is whether they start counting at 1 or at 0. All right? So when you look at this matrix and you say, hey, what's A of 1, 2? It's going to be 2. If I had slipped and been doing the Python way, right, maybe I'll put that in red. So if I was in Python land and I said, hey, A1, 2, that would instead be the number 3, right? Because I would have numbered the rows 0, 1, 2. I would have numbered the columns 0, 1, 2, 3. And then row 1, column 2 would now be this guy. And so I'd have this answer here, right? So it just tells you why it's so important to be careful, right? Now, one thing that'll make this consistent for both of the languages is if we're using things other than numbers to index the rows and columns. So you'll remember that when we talked about vectors, it's really a function, right, from any domain to a codomain. And we talked about saying, what if we have a vector and our vector is x, and really we're saying that, you know, my answer to survey question about skydiving, I gave a 2 on a scale of 1 to 10, and on the how much do I like knitting question, I gave a 7, and on a question of how much do I like cooking, I gave a 5, right? So in this case, I'm not even using 1, 2, 3, or 0, 1, 2, or anything else in order to index into the vector. I'm simply using these elements here, because really what we're saying is that this vector here, this x, is a function, right? And it's a function from the domain of, I don't know, we'll call this hobbies, to the domain of real numbers. And so if you give me a hobby, like knitting, I will give you the corresponding real number for this vector, which is 7. And if you give me a hobby, which is cooking, I will give you the real number, which is 5. Okay? Let's just review. Same thing is true for matrices. If I have this matrix A, And I have some elements here. Maybe I say it's 85 and 88 and 92, and I say 86 and 83 and 80, and I say 86 and 84 and 82. This is a 3 by 3 matrix, no matter how I count it, right? But maybe my rows aren't labeled that way. Maybe my rows are labeled Richmond, Fredericksburg, and Charlottesville. And my columns are named Monday, Tuesday, Wednesday, because you see, maybe this is a matrix giving me the high temperatures in those various cities and various days, right? And so now I could say, you know, what is A of Fredericksburg, comma, Tuesday? And the answer to that would be 83. Or I could say, what's A of Richmond, comma, Wednesday? And the answer would be 92, right? And then it doesn't actually matter how I'm numbering them because I'm not treating them by a number. Now, if you've taken All the Math Volume 1, you may remember this notation, right? So let's say I say C is the set of cities. And let's say I say D is the set of days of the week. And we'll just say that there's only 3 days of the week and only 3 cities for this example, right? So that A matrix here is actually a function of what to the real numbers? Well, it's a function of C cross D, if you remember this Cartesian product thing, right? What we're doing is we're saying, take every combination of an element from C and an element from D. So one such ordered pair is the ordered pair Fredericksburg, comma, Monday. Another element of the Cartesian product is Fredericksburg, comma, Wednesday. Another element of the Cartesian product is Charlottesville, comma, Tuesday, etc. There are 9 of them, of course, and that's why in our matrix we had 9 elements, because for each combination of a city and a day of the week, we're going to have an element, right? So again, we can treat a matrix like a function, just like we treated a vector like a function. That's really what it is mathematically in disguise. All this business about laying it out in a 2D space and looking at uppy, downy, and crossy, lefty, righty stuff, that's just for humans to look at, really. The underlying mathematical object is basically relating 2 different sets and the Cartesian product between them, so that for every pair that I can get an element from one set and an element from another set, we associate that with a particular number, right? Fun fact. One last thing just on notation, this drives me nuts, or I should say terminology. So matrix, as I may have said already in this lesson, probably have, the plural of it is matrices, okay? So you have 1 matrix, you have 2 matrices. There is no such word matrices, okay? So we don't use matrices as the plural, we say matrices. Even more important, because this just drives me nuts, is when students will say a matrice, okay? There's no such word matrice. And we tend to say, oh, if I have 2 matrices, what is the left matrice? Oh, okay, so it kills me when students say that. Don't say matrice, say matrix, and then we'll be showing respect for the object which we're going to come to know and love.